Find, with proof, a formula for Tn equals An plus Bn, where An and Bn are well-known sequences. Let T0 equal 2, T1 equal 3, T2 equal 6, and Tn equal this formula. The long equation that we're given in this problem is the recursive formula, which means we can calculate a specific term in the sequence based on the ones before it. Since we're given the first 3 terms, we can calculate the fourth to be 14. The fifth ends up being 40, the sixth 152, and so on. Let's take a look at some recursive formulas we know and their explicit counterparts. First, we have the Fibonacci sequence, where each term is the sum of the previous 2. The explicit formula is pretty messy, but here it is anyway. Next is the arithmetic sequence, where each term is the previous term plus a common difference d. We note that the explicit formula for each term is a0, the first term, plus the common difference times n minus 1. After that, we have the geometric sequence, which is like the arithmetic, but swap out all the addition for multiplication and multiplication for exponentiation. Lastly, we can also define the factorial recursively, since each term is equal to n times the previous term. This is just identical to saying that n factorial is equal to n times n minus 1 factorial. Now, if we take a look at our recursive sequence and expand a little bit, we can see that we have some constants times previous terms and some n's times previous terms, and a mix of both. The constants times previous terms correspond to the geometric series recursive formula, and the n's times previous terms correspond to the factorial's recursive formula. So that tells us that we're probably going to use these two in our formula. Let's look at some of the numbers in this sequence. A graph won't be very useful in this case since the function blows up extremely quickly, so a table of values will probably be more helpful. Here are the first 8 terms of t. We said a minute ago that we're probably going to use the geometric and factorial sequences, so let's also throw the factorial on here. We can see that the values are actually pretty close. The first term's only off by 1, but to keep it general, we'll call these distances d sub n. Let's look at all these distances by subtracting the second column from the first. Now we can observe that this function d of n is just powers of 2, 1, 2, 4, 8, and so on. So d of n is nicely equal to 2 to the n. And so, we've done it. Adding up these 2 columns gives us our original t sequence. So we get that t sub n is nothing other than n factorial plus 2 to the n. But the problem asks for a proof. To do this, we can use the given recursive formula and our hypothesized formula. We know that our previous terms can just be defined by replacing n with n minus 1, n minus 2, and n minus 3. And now we just have to plug everything in. As you can see, this doesn't even fit on the screen. After some nasty algebra, we eventually come to a true statement that 2 to the n plus n factorial equals 2 to the n plus n factorial. And so, that proves our hypothesis that t sub n does in fact equal 2 to the n plus n factorial.